Good evening, day, morning, good time, dear students. I hope you're feeling well and everything is alright with you and your families. I'm sorry for our lecture got a little late. That's because we have a lot of things to do, even we're not working directly with the students. So today's topic is gas mixtures. As you know, in heat power engineering or in the power engineering generally, we're working with the gases and the mixtures. For example, we are working with the steam, with the vapor, and sometimes vapor becomes partly it's not totally as in a gas form. Sometimes you have a liquid particle, so it's saturated liquid vapor. Other types of vapor or other types of mixtures. We can have gases with the solid bodies and other types. Today we're gonna consider the gas mixtures as a mixture of two ideal gases and the mixture of the real gases. And also we're going to study the real gases too. So let's begin. So consider a gas mixture composed of K components. It could range from 1 to well, to be honest, not the infinity. I guess the maximum value of the K could be like 5 or 6. In power engineering, we're considering not more than 3. Okay, the mass of the mixture is the sum of the masses of the individual components. It's logical, right? You have 3 gases. For example, you have 3 gases which weigh like 2, 5, and 10 kilos. If we put it in one volume, the mass of the gases will be as a sum of the masses of each gas. The mole numbers, which describes the amount of number of moles considered in any gas, is the sum of the moles of each gas. It's logically, right? The ratio of the mass is the mass of the individual gas divided by the sum of the masses, the total mass. And the mass fraction is the mole numbers of individual gas divided by the sum of the mole gases. For example, let's find out the mass and mole fraction of gas mixture. For example, we have a gas of O2, nitrogen oxide, oxygen, and methane. So the weight of each gas is 3, 5, and 12 kilogram. 12 kilogram. We must determine the mass fraction of each component, the mole fraction of each, and the average molar mass and gas constant of the mixture. The total mass of the mixture is the sum of each mass of the gases, right? So it's equals to 20. The mass fraction could be determined by dividing each mass by the weight of gas. So it's 3 divided by 25 and 12 divided by 20. It's logical. To find the mole fraction of the gas, we must divide the mass of the gas by its molecular weight, right? So we have O2, which is the molecular weight of the O2 is the of the oxygen is 60, so we have 2 oxygen, which means we have 32 kilograms per kilomole. And identically we can find the mass of the nitrogen which is around 14, and the molecular mass of the methane. C, which is carbon, has the molecular weight of 12, and the H4 have molecular weight of 1, and we have 4 of it. So if we sum the mole numbers, we will get the number of 1.022 kilomoles. And the mole fraction is the mole fraction divided by the total sum of moles, right? 1.022. So we can find the molecular weight of the gases by dividing the total mass by the total molecular moles. So it's 90.6 kilogram per kilomole. And the total mass, or we can sum the molecular fractions by the molecular weight, right? 32 multiplied by 0.092, and etc. Also, we can find the molecular weight of the gas constant of the specific gas, or in our case the gas mixture, by dividing the universal gas constant by the molecular weight. The PVT behavior of gas mixture during real gases. So the behavior of the real gas can be determined by the two laws. The first law is Dalton's law of additive pressures. So it says that the pressure of gas mixture is equal to the sum of the pressures each gas would exert if it existed alone at the mixed temperature and volume. So we have 3 gases, for example, and each gas has its own pressure. How we can find the pressure of each gas? We must imagine that there is one gas, and we can find it by the PV-RT, right? The equation of state. And we would sum the pressures, so we can find the total pressure of gas. I think it's logical. So there's another law, Amagat's law of additive volumes. The volume of a gas mixture is equal to the sum of the volumes each gas would occupy if it exists alone at the mixed temperature and pressure. So we can find the pressure by the volume, or we can find the volume by the pressure. Temperature is work for every gas. So real gases could be found by the equation of state. So we have a pressure, volume, universal gas constant, molar mass, temperature, and the compressibility factor. What does the compressibility factor means? It means that the real gas compared to the ideal one has the compressibility, which means that it compresses, it changes its volume depending on the environment. So to find the compressibility factor, we must use the Amagat's law or the law of Dalton's law. For example, a rigid tank contains 2 kilomoles of nitrogen oxide and kilomoles of CO2 gases at 300 kelvins and 50 megapascals. Estimate the volume of the tank on the basis of ideal gas equation of state, K's rule, compressibility, and Amagat's law, and compressibility, Dalton's law. The composition of mixture is given. The volume of tank is determined using different approaches stated in each section. Okay, when the mixture is assumed to be having ideal, the volume of the mixture is determined by the ideal gas relation for the mixture, right? So we have the 8 kilomoles because this is the sum of the kilomoles. Universal gas constant, and the temperature, and we have a pressure here, so it's 1.32 cubic meters. To use K's rule, we need to determine the pseudo-critical temperature and the pseudo. So I don't know where do we stop, right? But I recommend you to closely watch these formulas, and after the 3 iteration, we'll get we'll get the iterations of 0.64, which are pretty close with the other calculations. Thus, we end the today's lecture. I will divide this lecture by 3. The rest of the lectures, we will have 5 lectures. So I am giving you the home task as following. Each of you, you're 12 people, right? So we have 200 and 120 minutes, which means that we have at least three lectures. But including the facts that we have a time to prepare in others, I'm giving you the time to prepare for the lectures by yourself, which means that each of you, will prepare one lecture for 10 minutes. You can take any topics, including the past ones, but I recommend you to prepare for every lecture. That's the we will finish our lectures by the gas vapor mixtures. I will finish it, and the rest of your lectures should be prepared by yourself. So we have 3 lectures. End of course, I will prepare it myself. So we have 11th, 12th, and 13th lecture prepared by you, which means that we have 50 minutes. We have more than enough, I think. So the first person who will prepare we will prepare by the schedule of preparement will be by my journal. So we have Aytumar first, Tolganay second, Opan, Camila, Alibek, Diyar, Aychurek, no, not the Alibek, Sultanov Rahat, and the last one will be Shomagambetov Rahat. We will divide you by the 3. So we have Aytumar, Tolganay, Opan, and Camila for the 11th lecture. Diyar, Aychurek, Obike, Rahat for the 12th lecture, and Baghdad, Madina, and Rahat will prepare for the 13th lecture. And I will rate you by your lectures. And that's it, I guess. That's the end. Thank you very much for your time. Please feel free to ask any questions directly by any social media that you have, or you can add your feedbacks on the today I will ask you to add feedback in the Polytech online service. Uh,